IPS, which is grams of product formed per gram substrate consumed, is nothing but small f into the molecular weight of the product divided by the molecular weight of the substrate. So these give us two additional formulae, two additional relationships. So now how many total relationships do we have? We have 5 now. So we are still short. In other words, you can say that we had two elemental balances, one measured quantity based on RQ, another two measured yield coefficients, right? So 5. So I suggested to you that we have to worry about a more general concept which will supply us that missing 6th relationship. And all of these were based on a concept that, let us term it today, called available electrons. Or in other words, we must balance, we must carry out an available, within quotes, an available electron balance. And that will give us the 6th item of information. So what do I mean by this? Basically, the available electron balance means that, please note down if you want, that the electrons that are available for transfer to oxygen in the aerobic system, they are all conserved during the metabolic and the growth process. In other words, what available electrons refer to are the number of electrons that are available for transfer to the oxygen upon combustion of the substrate, complete combustion of the substrate to CO2, H2O, and other nitrogen containing compounds. So essentially, if we look at the available electrons that are in organic material, we can estimate them very simply from the valence of the various elements that constitute them. So for instance, for carbon, we have 4. For hydrogen, 1, there are -2. For oxygen, 5 for phosphorus, etc. So suppose we were to take ammonia, then the number of electrons, available electrons, is taken as -3. For molecular nitrogen is the source, that's 0. So what we define to calculate the number of electrons, normally your book in chapter 7 also does that. You can read also from that. The words and the explanations will be different, but basically they define what is called the degree of reduction. And we can specify a degree of reduction for every species participating in the general cell growth equation for aerobic systems that we wrote in the beginning of this class. So degree of reduction is given the symbol gamma. Okay, and this gamma is defined, please, this is important. This gamma is defined as the number of equivalents of available electrons, defined as the number of equivalents of available electrons that are present in a material, in a quantity of material that contains 1 gram atom of carbon. For instance, for biomass, if we have to do, it already was the stoichiometric coefficient, so we don't need to divide it through. But if we have to look at the available electrons in substrate, we will have to divide through by, I mean, we will have to calculate the degree of reduction. We have to divide through by small w. So for instance, if for the substrate, we have to calculate the number of available electrons. So it would be nothing but 4 times small w, which accounts for the carbon, plus small x accounting for the hydrogen, minus 2 times y, taking into account the oxygen, minus 3 times z, which is for the nitrogen. And now the degree of reduction of the substrate gamma, and let us give it a symbol S, subscript S. So gamma S is the degree of reduction of the substrate. It is nothing but 4 times W plus X minus 2 times Y minus 3Z, whole thing within brackets, divided through by small w, because the degree of reduction is defined per gram atom of carbon. So this had small w gram atoms of carbon in the substrate as per our stoichiometric equation CWHXOYNZ. So therefore the degree of reduction is as I told you. Now in a balanced growth equation, the number of available electrons is always conserved, because every element anyway we are conserving. So although we cannot use capital H and capital O, I mean oxygen and H as in a balance, we can definitely use the number of available electrons or the degree of, or and balance them. That is a very general balance. In other words, if we have so many available electrons from substrate, let us say, we can either transfer them to oxygen, or we can transfer them to the biomass. Of course, I mean, CO2, it will all cancel out, because CO2 is plus 4 minus 2 into 2, so it doesn't matter. Or we can send it to the extracellular product. So this balance is a very general balance, right? So H2 also doesn't come into the equation, because 2 into 1 minus 2 into whatever is the gamma is 0. So that won't come in the equation. So all we need to worry is how many available electrons are there in substrate, and what fraction of those available electrons goes to biomass, what fraction goes to product, what fraction goes to oxygen. Okay, so now suppose I tell you that using this concept of available electrons and taking into account product synthesis, where the product is different from the biomass, suppose I ask you to find the overall electron balance for the general equation that I did. What will you do in terms of the degree of reduction of substrate, the degree of reduction of the biomass, gamma subscript B for biomass, and degree of reduction of the product? Can you tell me how many available electrons are there on the left hand side, and how we will balance them, considering that these electrons are shared among various species, which I just outlined? So if gamma S is the degree of reduction of the substrate, how many available electrons did it have? Small w into gamma S, right? So that is the number of available electrons which are available for transfer from the substrate. Okay, how many of these available electrons went to oxygen?
Sir, can you please share your screen?
I don't have the screen for this because my notation is different from the book. But if I were to, you can directly take the same equation is there in chapter 7 of your source material, but that's not the notation I used. So unfortunately, can't, otherwise everything will change. I mean, we'll have to change the subscript for nitrogen source as well as product, because the book doesn't, and the book doesn't use the Roman alpha, beta, gamma, delta, etc. That's a problem. I mean, it uses our Arabic, I mean, whatever A, B, C, D, F. So every notation will become different. So general equation you write, no, CWHXOYNZ plus A moles of oxygen plus B moles of nitrogen source, which has the empirical formula HGOHNI. This goes to C moles of biomass. Biomass we have always from the beginning given per mole per gram atom of carbon, and with symbol alpha, beta, delta for H, O and N elements, and then plus D moles of CO2 plus E moles of H2O, and now F moles of the product with JKLM as the indices. This is our balance. So now you have to look at this balance. Isko aap likh lo, and now if the degree of reduction of the substrate is gamma subscript S, then the number of available electrons that it can transfer to all these different components is all these different species is nothing but small w into gamma S, because gamma S was also always defined per unit per gram atom of the carbon. Now, I asked you how many of this available electrons go to oxygen. You know the stoichiometric coefficient of oxygen. And you also know its valence. Because we said that the number of available electrons is calculated is -2 per oxygen atom. So for oxygen molecule, there will be 4 of these. So 4 times A small a is the number of available electrons that you will transfer to oxygen. Correct? Of course. So now similarly, tell me for the biomass. On the same lines, see, what I am saying is these available electrons that are available for transfer to oxygen from substrate to product from substrate to biomass from substrate, all this has to be conserved, right? This has to be balanced, right? During that growth equation, this has to be balanced. So I'm just trying to balance those electrons. So just now you told me how many available electrons are there from the substrate. So these can be transferred to oxygen also, some part of it at least. So that you just now told me is just 4 times small a. So now I asked you how many of these available electrons go to the biomass. You know the degree of reduction of the biomass. You know the stoichiometric equation. What is the stoichiometric equation governing the biomass? Small c. So how many available electrons are there in that biomass? Naturally, small c into gamma b, where gamma b is the degree of reduction for the biomass. See, the degree of reduction is something that your book will tabulate for everything. Right now, of course, you have to assume. I mean, for nitrogen and all, we assume NH3 is the reference, but it's tabulated in your book for gamma S, gamma product. For nitrogen, NH3 is always conventionally taken as the reference, but in principle, because see, when you why they take this as reference is NH3 gives you a degree of reduction of 0, right? +3 for the H and -3 for the N, so it's 0. Degree of reduction of CO2, H2 are already 0. I just did it for you. I mean, you can see it for yourself. So therefore, generally we take this reference as 0. That is why conventionally CO2, H2O and NH3 are taken, and these all have degrees of reduction of 0, so we don't need to worry about them. But of course, if I generally CO2, H2O, so always they will be there. But nitrogen source we can change, and then of course you have to the tabulated degree of reduction. If NH3 is not the source, will of course have a finite value and not a value of 0. Okay, but right now, so these are all tabulated with respect to ammonia in chapter 7 of your source book. So C times gamma B is the number of available electrons that are transferred to biomass. Now, what is left? Product is extracellular product is left. इसको बताइए आप. So you had W times gamma S of substrate. 4A went to oxygen. C times gamma B were conserved in the biomass. And now how many available electrons are captured by the product? What is the degree of reduction of the product? Gamma subscript P, right? That will be tabulated with respect to ammonia as the reference. So you will get a value from one of the tables in your book. Now, if degree of reduction, which I told you is the number of available electrons, okay, per gram atom carbon, right? That is how we define the number of, degree of reduction of gamma, right? The number of equivalents of available electrons in a quantity of substrate or product or what have you, biomass per gram atom C. So how many gram atoms of C are there here in the product based on the equation that you just now wrote? You have, okay, let us go a little differently. What was the degree of reduction of the product? Gamma subscript P. How many moles of product were produced? Look at your balanced, your general equation that you just now wrote at the beginning of the class and which we reiterated, no? Just look at the equation. You produce C moles of biomass, D moles of CO2, etc. So how many moles of extracellular product are there in your equation?
F moles, right?
Exactly. So we must multiply gamma P by F. But is that all? No. So what are we missing? So if we want to find out the number of available electrons that are present in the extracellular product, we will take the degree of reduction just as you said, and as Vishantan said, we will multiply it by small f because that many moles of the product were formed. But since the degree of reduction is per gram atom, no? So how many gram atoms were there? See, in your balance, in the equation, general equation that you just now wrote, which you extended to include the product formation, उसका क्या हो stoichiometric coefficient क्या लिया था आपने? F आपने लिया था, लेकिन उसमें उसका empirical formula क्या था? What was the empirical formula of the product?
HKOLNM.
Right. So what were the per gram? We are interested in the gram atoms of carbon. कितने gram atom of carbon है वहाँ?
So FJ.
Exactly. So it has J gram atoms of carbon, and F is the stoichiometric coefficient. So F into J into gamma subscript P is the number of electrons that were transferred from the substrate to the product. So now when product synthesis is occurring and as it is represented as given in the general equation that I dictated to you, so the available electron balance will be W into gamma S is equal to 4A plus C times gamma B plus F into J into gamma P, right? So normally what we do is, see, gamma S, gamma P, gamma B are all known and they are tabulated in fact in your book. So we can use this to find small a we do not know, and that is essentially your oxygen load. That is your oxygen demand.
Just a second, I didn't understand what is the difference between gamma P and gamma B.
See, gamma B is the degree of reduction of the biomass. And gamma B, that means is the number of available electrons that are there in 1 gram in a quantity of biomass which contains 1 gram atom carbon. Similarly, the product which contains 1 gram atom carbon contains available electron, that is gamma subscript P, right? So degree of reduction is the number of equivalents of available electron in that quantity of material which itself has 1 gram atom of C. So that is there, J moles are there in product. In biomass, it's only 1 because by convention we wrote it like that. In substrate, it had W, so you have to multiply it by that. And since we started with 1 mole of substrate, we just multiplied it by small w. But here we had a stoichiometric coefficient small f. So you multiply it by J, the degree of reduction of the product, times F, just as Vishantan dictated to us, right? So now gamma B, gamma P, gamma S, they are all known to us. And what is really interesting, and this is a very useful equation because very general balance. So this will give you the 6th equation that we want for calculate the 6th, the sixth unknown that we added with inclusion of small f, and we can actually obtain the oxygen requirement because we have said that this requirement is directly related to the number of available electrons for transfer to oxygen, right? So this oxygen load or oxygen demand is essentially given by or represented or given as a measure of that oxygen demand is small a, the stoichiometric coefficient that modulates oxygen O2. So you can transpose this equation and obtain small a from this. So small a is nothing but 1 by 4 and within brackets all the things of available electron W times gamma S minus C times gamma B minus F into J into gamma P. That is your oxygen demand. So if you know the organism, that means you know gamma B. If you know the substrate, that means you know small w and you of course know the degree of reduction gamma S. And if you know the product, which means you know it has J moles of C in it. So you know J and you know gamma P, the degree of reduction of the substrate in the cell culture. Then you can calculate the yields of the biomass and the product. That is, you can get small c and small f. I mean, they are related through the equation that you just now did with available electron balance. Is that clear? Now, this is a very important equation. So the equation was A is equal to 1 by 4th and within bracket W gamma S minus C gamma B minus F into J into gamma P, right? But now what we can do is we can determine what is the maximum possible yield. That is the best part about such balances. In other words, we can find out, suppose, what is the maximum if we let us express everything in terms of fraction, that then maybe we can easily, you can see when it is a maximum, because the maximum is then 1. So what I suggest is the same equation that we just now did. Just look at it as a fractional allocation of available electrons. Suppose there was only one available electron in the substrate, then what fraction of the available electrons went into oxygen? See, your equation was W gamma S is equal to 4A plus C gamma B plus Fj into gamma P. So if I divide through by W gamma S, that is nothing but my fraction of the available electrons that are there in substrate, how they are shared, and what fraction is the available electron that is transferred to oxygen, biomass, and product. So the left-hand side is 1 because you divide it through by W into gamma S. And the right-hand side had the 3 terms. So oxygen, the fraction of allocation of available electrons from substrate to oxygen is nothing but 4A divided by W into gamma S. Similarly, the fractional allocation to biomass is C times gamma B divided by small w into gamma S. And finally, the fractional available electrons found in product is F into J into gamma P divided by W into gamma S, right? So this is your, so the first term on the right hand side then is the fraction of available electrons transferred from substrate to oxygen. The second is the fraction of available electrons transferred to biomass. Third is the fraction of available electrons transferred to product. Now, what I suggest is use this, since all of the three have to add to 1. So now use this relationship and see if you can obtain the upper bound for the yields of biomass and product from substrate. And that's our last topic, essentially. So derive this fractional equation. 1 is equal to 4a upon W gamma S plus C gamma B upon W gamma S plus Fj gamma P upon W gamma S, and see when the fraction of available electrons in the substrate which is transferred to biomass, let us say, can be maximized. It will be maximized when that fraction is unity, isn't it? So put that fraction equal to unity, and that then is the maximum yield, or rather you can say that is the maximum value of the stoichiometric coefficient which modulates biomass production, so small c. So you can get a maximum value for Cmax from maximizing this fraction. Okay, we will complete it next time, but my point is just go through this available electron balance with the help of your book. Of course, notation there is different, doesn't matter. And let us discuss if there is any difficulty, and I shall then obtain for you we can all do this together, because it's just a maximization of and obtaining the maximum possible yield, and that is a very useful thing, because that sets a limit, upper limit on what you can find in any fermentation. Okay, because the stoichiometric coefficient can always be converted to a biomass yield, because you know all the molecular weights, you know all the mass units, you can always convert one to the other, right? So we can very quickly calculate an upper limit for the biomass yield. That is a very useful thing. Okay, we can repeat this part tomorrow, but please look at the available electron balance, because that gives us an independent equation, and it's an equation that is very general, and you can always trust it compared to simple hydrogen or oxygen elemental balance. Okay, so what we have done today is added product stoichiometry, product formation, giving us an extra unknown, but then we said we also have, in addition to the RQ and the 2 yield coefficient that I discussed, we also have a very general available electron balance, which I would completely trust. Okay, and I'm not saying this available balance is independent of the elemental balances, but since we did not include hydrogen and oxygen in the elemental balance, I mean, removed them, the electron balance is where we can always include. So it will always give us a very general set of equations. Okay, so let us rewrite once again, let us summarize that on Wednesday, and let us calculate the maximum possible yield, and then we can see how it can be applied to actual data. The other thing I want you to do is just revise heat of formation, because any reaction, the heat of formation into the stoichiometric coefficient plus minus sigma, etc., is the delta H naught of the reaction, right? In the standard state of 1 atmosphere, etc., 298 Kelvin. Okay, because heats of formation data are all available for so many chemical reactions, and I mean that you can all. I mean, I don't have to give it to you, and that's something that we need to worry about on Wednesday. Okay, इसको ये revise कर लो, and then we should be able to complete everything by Thursday. And by the way, you have to form groups, and groups का every group of 6 has to have a leader. So please.
Yes, sir. That I had the same doubt. Like, where do we have to submit the groups?
Give it to me before Thursday.
No, sir. Like, how do we submit it? Like, do we collectively form a document and then mail it to you?
No, you just have to tell me. See, the group leaders of this each will have 6 people. Each one will have a leader. So we will have something like 12 groups. Each one has to make a presentation starting 27th because we have only 3 classes or something. So 12 minutes or 10 minutes is the maximum. 12 minutes would be looks like of a presentation. Each one can you can assign, and then the leader has to and then let us do it alphabetically based on first name of the leader, in each of the groups. And 27th, I'm back on 25th, and then we can start that. So you can just form you can form group of 6 based on whoever you want to include. Okay.
Okay, sir. Sir, sir, I can make a list and submit it to you.
Don't give it to me today. Let us first finish the course. By Thursday we'll be finished, and then
Okay.
Thursday only you take your time and give it to. If you can do this by Thursday, I'll be very happy.
So basically, we just have to select a certain subtopic or topic and then make a
Yeah.
short
You have
presentation.
everything. Whatever we have done whatever we do to Thursday, that is your portion for the major.
Okay.
Okay. So, all right. Let's complete this part on Wednesday and then move to finding the heats of reaction, because that's something that we haven't yet discussed, and that's the last part on the chemical reaction energy balance. Okay. Thank you.
Thank you, sir.
Thank you, sir.
Yeah. Thank you very much.
Thank you, sir.
Thank you. Yeah.